omega to r, where omega is contained within n. So if we have that p is bigger than n, then we have that the function is actually Holder. So f is 1 over n minus p Holder continuous. And we mentioned this before. This is not. This is kind of not that surprising. It comes from the fact that if we have enough integrability of the derivative, then expressions like this expressions like this are actually integrable for every x just by doing Holder's inequality. And once things like this are integrable, then we can integrate out on lines using the curve area formula, and then we'll have that the integral of the gradient along lines actually is finite, and then we can connect the difference between two functions along lots of these intersecting lines. So, I mean, that's a very brief sketch, but actually let's write it like this. So this thing, like this, is less than infinity, so not surprising. If you mess around with this kind of inequality and just do elementary arguments, you'll see you'll get some kind of Holder estimate, maybe not the optimal one, but enough to give you some reason why this isn't such a surprising thing. And if, let's study it this way, if omega is Rn, and we have that p is between 1 and n, oops, like this, then we don't have okay, so this is just a sketch of an argument, but if you, okay, so do you sort of agree that if we have an expression like this, then, and we have enough integrability, then this thing will be actually finite? Okay, and this is, so in the plane, this is the kernel of the curve area formula. So let me put this over here. So if n equals 2, then if we do this, the integral around whatever, it's not even, yeah, let's do it. The integral around a ball of radius x of gradient f of z over mod z minus x, like this. dz, this is like the integral from 0 to pi of the integral on 0 to r e. So I'm identifying e to the I theta as this vector cosine of theta sine theta, like this. Let's do it like this. This is equal to this. This is the h1 measure along this interval, and this is integrating with respect to this angle. Okay. So if this thing is finite, then that means that we have lots of these lines. Actually, this is more than finite. This will be bounded by the Holder norm of this, by the LP norm of the gradient. Right. So we have lots of these lines for which this thing is bounded by some specific quantity. Right. So we have lots of lines emanating out like this, for which this is a nicely controlled quantity, so at least 90% of those lines. So if we have 2 of these points for which this is true, then some of those lines have to intersect. Right? So if this is a point x0 and this is a point x1, we're going to have control over at least one pair of lines emanating out from both of those points, like this, to some common point. Yeah? And then we can consider the difference between f and this common point. Let's call it z. Now let's call it x tilde. So if we then consider f of x0 minus f of x tilde, we can control it by the integral on this line. And consider f of x1 minus f of x tilde, control it by the integral on this line, yeah? And that thing rounds above f of x0 minus f of x1, like this. So write the argument out for yourself. For sure, you can find these intersecting lines. You're going to apply Holder's inequality to each one of these lines here, and what should fall out will be some exponent. It might not be the optimal exponent, but it will be some exponent. Yeah, cool. All right, pleasure. So if p equals n, p is between 1 and n, then we don't have such good things, but we do have good things in the sense that we have improved integrability, that the integral of the function, so we're doing this over all of Rn, up to this exponent, I'm going to define as p star of f dx, is bounded by the integral of, well, I think I should put 1 over p star integral over Rn of the gradient of f to the p dx 1 over p, where p star equals np over n minus p, like this. Okay. So as p gets close and closer to n, this number gets bigger and bigger. We get a big improvement of integrability. Yeah. Cool. And this is for functions in the entire domain. So in particular, this thing here vanishes towards the boundary, which is why we don't have a term. We just can bound this by the gradient like this. If we have a different domain, potentially a bounded domain, so generally, if omega is a domain with a nice boundary, is a Lipschitz boundary, so we can actually extend it to a Sobolev function defined on the entire Rn. Or maybe has Lipschitz boundary. Then we have the p star norm on this thing is bounded by the Sobolev norm. Of omega like this, with some constant obviously, and this constant depends on the domain. With C depends on the domain like this. Yeah? Okay, so that's typically what's called Sobolev inequality, or maybe this is called Murray's inequality in the case when p is bigger than n. This is Sobolev embedding theorem. And it seems a bit dry, but it's, I mean, the first time I saw it, I didn't see what the point is, particularly this part of it. I thought that, who cares about more integrability? But as I hope I showed you last time, once you have this tool, then you can increasingly get more and more integrability by having more and more gradients bounded in L2. In the case when we do the Laplacian, and we did this Cacciopoli argument to control the higher gradients by lower ones, and therefore we are able to get enough integrability of the gradient so that we can apply the case when p is bigger than n and get that the gradient was Holder. That's how we prove that weak solutions of the Laplacian via this elliptic regularity machine are as smooth as you like. All right, cool. So that is this theorem. Now we're going to talk about Poincare inequalities, which we've mentioned a little bit before, and we're going to do a kind of a slightly more strong version of the Poincare inequality, which is sometimes called Sobolev Poincare inequality. So, Sobolev. So suppose we have some function u belonging to W1p, omega. When we're taking scalar valued functions, there's no real loss in generality in doing this. So suppose we have this, then if we have the ball of radius 2r, no, r would be enough, ball of radius r contained within our domain, then for any q between 1 and this Sobolev embedding exponent p star, we have the following is true, that the integral of the average of a ball of radius x0 of f minus its average on the ball of radius r at x0, so I'm going to write it like this, r of x0, like this, raised to the power q, 1 over q, is bounded by a constant. This is a universal constant. It doesn't depend on anything. It's just a fixed constant in cases where it's calculated. Well, this is, I think this case is where it's calculated. And I've switched from U to F, damn it. And this is to P, 1 over P, okay? So the classic Sobolev inequality, you would have P and P here. But it's also true that if we take some Q, which is less than the Sobolev exponent, then this is also a true fact. And this is a stronger statement because by just Holder's inequality, if we have Q, which is in this which is between P and P star, then this thing controls the P norm. Yeah? And this stronger version of Poincare inequality is what we'll need in the proof of Sverig's theorem. Okay, so my plan for today is to, as quickly as possible, prove this, and then we'll start the proof of Sverig's theorem. All right, everybody clear on what we're doing and what we've talked about so far? Everybody good? All right, I'll raise the board, and we'll get to work on this. Okay, so proof. Special case. Consider first. X0 to be 0 and R to be 1. And suppose this is false. So there exists a sequence, let's call it Fn belonging to W1P, such that when we do this thing, the LQ norm of F, so F tilde is going to be the average of F on a ball of radius 1, I'll write that in a second. And we have the Q norm on the ball, then this thing is not controlled by above, so this will actually be bigger than 2 to the n of the norm of the gradient with respect to P on the ball of radius 1, like this, where the sequence, yeah, there we go. Thank you. Where f tilde n equals the average on the ball of radius 1 of our function fn dx, like this, right? So you guys agree that if the statement is false, then we have a sequence like this. Yeah? Okay, cool. Then let us rescale. So define g of n to be equal to this function f of n of x minus its average divided by the LQ norm of the function minus its average on the ball. Yeah? So in particular, what we have is that this function has an LQ norm on the ball exactly equal to 1. Yeah? And we also know that if we take the gradient of this guy right here, then we're just going to have the gradient of fx over this constant like this, fn minus fn tilde, LQ would be 1. Yeah? So we have that when we take the LP norm of this gradient like this on the ball of radius 1, that's the same as the LP norm of Fn on the ball of radius 1 over this quantity Fn minus Fn tilde LQ on the ball of radius 1 like this. And we have, by assumption, that this guy is bigger than 2 to the n of this guy like this. Yeah? So in particular, this thing is less than 2 to the minus n. Yeah? Cool. So we have a sequence of functions whose gradient is controlled, right? This theorem is interesting in the case when we take the Sobolev exponent, or the exponent q as close to the Sobolev limit as possible. So we're going to, so if we can prove it for such q, then it's true by Holder for lower order q. So we can without, for lower value q, so we can without loss of generality assume that q is actually bigger than p. Yeah? So recall q is any number between 1 and np over n minus p, like this, yeah, where p is less than n. Yeah. So this thing will always be bigger than p, this exponent right here. Yeah. So we can take something that is bigger than p, but less than this exponent. Oh, and this is not including like this. So assume. I mean, this is not a very important point, but it's just makes things a bit neater. Okay. So if we do this, then what we have from this stuff is that we have a bounded sequence in W1P, because the gradient's controlled in LP and the norm of the function's controlled in LQ, which by Holder controls it in LP, right? So bounded sequence in W1P, and let's put it on the ball just to be absolutely explicit. And so there's some subsequence that converges weakly. We have GKN converges weakly in W1P to G. And as I've said before, we can also assume that the subsequence is such that the functions converge strongly, because by relic compactness theorem, once we have that the gradients are uniformly bounded in LP, then for some subsequence, the actual functions themselves will converge strongly in LQ, where Q is anything less than the Sobolev exponent. Yeah? So, and by relic, yeah. Can assume that GKN converges in LQ on the ball to the limiting function G as well, like this. Cool. All right, so with these things, what we know? We know that these gradients in LQ are tending down to 0. So it's not surprising that the weak limit will also be 0. And let's see that. So claim this function g is in Sobolev space by this weak convergence, but the actual gradient of g is 0 almost everywhere, because for any test function, let's say f belonging to the p, so this is the Holder conjugate p prime norm of the ball into, I think we're doing this, are we doing this in Rn? Yeah. I guess we're doing this in Rn, right? So the gradient's in Rn, so for any of these guys, if we consider the following, well, okay, let's do this in 2 steps. So, no, we don't have to. Let's do it in this 1 step. So for anyone like this, then weak convergence means the following, that when we take gn dot product with this guy, whoops, gkn, the limit as n goes to infinity of this is gradient of g dot product f dx. That's what it is. Yeah, that's the definition of weak convergence. Cool. But the integral of the gradient of g kn dot product f, I should put on the ball, dx. Biholder is less than the gradient of gkn lp on the ball, and then f itself lp prime on the ball, like this. And then this thing is going down to 0, right? So the limit of this thing is just, let's put a value around this, the limit of this thing will have to be 0. So therefore this thing is equal to 0 for any choice of f. Yeah? So E1 gradient of g dot f dx equals 0 for all f p prime E1 into Rn. And that's exactly saying that this function is 0. Right? If we test any LP function, vector valued LP function, against all LP prime functions, and every time we do it we get 0, then that function has to be 0. Yeah? So gradient of g is 0 almost everywhere. Everybody happy? Yeah? Cool. So that's what we know about the gradient of g, but we also know that the norm of g itself is non-trivial, because we've set this up so that the LQ norm of the sequence is always equal to 1. Yeah? The LQ norm of the sequence is always equal to 1. Let's put it up here. So let's do this inequality. So if we do the LQ norm of the ball minus the LQ norm of the sequence, like this, then this thing, my triangle inequality, is less than this thing, g minus gkn, LQ norm on the ball, like this. Yeah? And then that thing is going down to 0, because that's what we have from relative compactness theorems. That goes to 0. This thing is always equal to 1, right? So then this implies that the actual LQ norm of g on the ball is 1. Everybody agree? Yeah? All right. And final interesting thing about limiting function g is that the average of g is equal to 0. And that's true because that's how we set this up. So we have the integral of the ball gn of x dx is equal to 0, like this, yeah? Because that's how we set this up. It's fn minus its average divided by some constant. Thumbs up if you're with me here. Yoko, you don't look convinced. No, that's just the integral of the function. We're taking the integral of the function itself. Yeah, so let's see what happens when we integrate through this. So if we integrate this, then we're going to have the integral of the polar radius 1 of fn of x minus its average on the ball dx, and all of that is over this constant fn minus fn tilde, like this. Right? And then this thing is just equal to 0 because it's oh, I need to average. Sorry, I need to average like this. Yeah. Cool. All right, so then this thing is equal to 0, like this. And then again, since Gn is converging strongly to G in LQ, then in fact, weak convergence would be enough in this case. This implies that the average of G itself, dx, is equal to 1. No? No, is equal to 0. Sorry, is equal to 0. So this is equal to 0. We have strong convergence, so the average of G is equal to 0. Cool. All right, so we have an interesting function. We have a function whose gradient is equal to 0 everywhere, yeah? Almost everywhere. It's in Sobolev space, W1P. Its average is 0, but its LQ norm is equal to 1. Okay, I'm going to raise the board. You guys think about that. Tell me interesting things about this function with all these properties. Yeah, G should be identically equal to 0. Yeah, but implicit. Okay, so implicit in this is a theorem that you probably know. Maybe Jaime knows also, that if we have a function in Sobolev space whose gradient is equal to 0, so the LP function, that is, its gradient is 0 almost everywhere, then that function is constant on connected domains, which is a slightly more non-trivial thing than if you had well, more than slightly, than if you have a smooth function. If you have a smooth function, then it's obviously true by the fundamental theorem of calculus, right? You can just take 2 points, you take the integral of the gradient between them. If the gradient is 0, then that integral is 0, so those 2 points are the same. Yeah? But we're in Sobolev space, so we don't have pointwise things happening anymore. Yeah? But we can still do something, and let me just briefly sketch that. So we have that gradient of G equals 0 almost everywhere. G belongs to W1P of the ball. The average of G is equal to 0, but the LQ norm of G is equal to 1. And we're going to model this proof of how we would do it if we had a smooth function. But we're going to use facts about LP functions. So have you guys heard about the Lebesgue property of LP functions, that if we have almost any point, then if we take the average over a small ball, then that average tends to some limit, and that limit is what we call the precise representative. Have you seen that kind of thing? Jaime, have you seen that kind of thing? Yeah, it's a Lebesgue point. Yeah, it's a Lebesgue point. It's exactly that, right? So suppose that, well, the only way that this is true is that if we have a set of positive measure where G takes values which are different than G on some other set of positive measure. So in particular, if G is not equal to 0, or if G, yeah, okay. So if G is not a constant almost everywhere, then there exists at least 2 points that we can pick almost everywhere for which we have different values. Yeah? Suppose G is not constant, and if it is a constant, its zero average has to be equal to 0. In this ball, then we can pick the big points A, comma B inside the ball, for which which are the big points I already wrote that. Points such that G of A, okay, let me be more precise, such that G of A is equal to its value and it's not equal to G of B. So the limit as R goes to 0 of the average of the ball of radius R around A of G of X dx is not equal to the limit as R goes to 0, the average on the ball of radius B X dx. And we're going to call this G tilde of A, and we're going to call this G tilde of B. Okay, cool. So, if that's the case, then let's draw a picture. This is A, this is B. And we have a direction, let's call it direction V, which is B minus A over B minus A. Then let's create a test function that is a function that lifts off in this direction. So it's a function that will be supported on a thin strip around this line, like this. So this is our thin strip. It's going to have radius R. Oh, I should say thickness R. And then let's lift it off like this. So what that means is that this function we're taking, just think of it as being the distance away from the boundary of the thin rectangle. Yeah. So if we do that, then the gradient points in this direction and in this direction on the sides, and it points in this direction and in this direction on the top and bottom. Yeah, just the distance away from the boundary. Yeah. So let's take this to be our test function phi. It's not smooth, we can convolve it, we can make it smooth so that these edges go away. That's not too big a deal. And then let us test our function g against this test function phi. So, or at least against the gradient of this test function phi. So the integral of g let's think how I want to do this. Yeah, let's test this against the partial derivative of phi in the direction v. Right? We can take the partial derivative in any direction that we want, of course. Right? And then by property of Sobolev functions, this should be this. The partial derivative of the gradient of g in direction v, which is the same as the gradient of v dot product with this direction v. So let's write it like that. A gradient of this dot product v times phi dx, right? This is the definition of weak derivative. Yeah? But what is this thing? This is the partial derivative in direction v. So in these sides of this thing, it's just 0. Yeah? Because this test function phi is not, it doesn't have any derivative on these sides in direction v. Yeah? Thumbs up if you see what I mean. So here we get no contribution from this. Yeah? So d phi by dv is equal to 0 on these sides. Yeah? But here we have real things happening. So d phi by dv is 1 here because we're lifting off. And here d phi by dv is minus 1 because we're going down. Yeah, we've taken our function just to be the distance away from the boundary, so it's lifting off with norm 1. Yeah? Okay, cool. So let's think about the size of this little region. Since we set this up to have thickness r, then this thing here this little so this thing here, this little triangle here, has got area kind of like r squared, or r to the n. So I'm implicitly doing this in the plane, so let me say that now. So let's do this n equals 2, special case. So then the area of this thing is approximately r squared, yeah? Because it's a triangle with its sides approximately equal to r, right? So this thickness is r, so this side is about r, and this side's about r, so the error is about r squared. And the same for this, yeah? Everybody happy, yeah? So then let's see what we get out from this. So on this left-hand side here, we have, let's call this triangle T1, and let's call this triangle T2. So then this thing, since this guy vanishes except on T1 and T2, it is like the integral on T1 of g times 1 minus the integral on T2 of g times 1 again. So this is minus 1, so it's like minus the integral of g on T2. Yeah? Yeah. And then this thing, happily, is just equal to 0, because the gradient's equal to 0. Yeah? Cool. But then we can divide everything by r squared, so this implies that integral of T1 g dx minus the integral of g dx on T2 over r squared is equal to 0. Yeah? But if we set this up so that the center of our triangle is exactly point A, and the center of this triangle is exactly, so the center of this triangle is point B, and the center of this triangle is point A, then this thing is controlled by the average of the ball of radius, whatever, 2r on A. Yeah? And so is this thing controlled by the average of the ball on radius 2r around B. Yeah? Yeah? So if we're a bit more sophisticated and we don't just divide by r squared, we divide by the average of this triangle, and actually this triangle depends on radius r, so let's call the triangle T1 and TR2, and then let's divide by the area like this. Then as we let r goes to 0, so then this means that g tilde, so this thing will tend to g tilde of A minus g tilde of B is equal to 0, contradiction. Do you guys see what I mean? Yeah. So what did we do? What we did is a kind of a test function version of the fundamental theorem of calculus, right? In the fundamental theorem of calculus, we would integrate along a line and would say, okay, the difference between the endpoints is the integral of the gradient along the line. We did a kind of version of that where we set up a test function that goes along a line that is mostly charged only at the top and at the bottom, you know? Yeah. And when you put it directly into our definition, and by the property of having Lebesgue points, that means that on almost every point, we do have a reasonable average of what's happening as we integrate around the ball divided by the area of the ball. It is tending towards some particular thing. The function is averaging out to some value. We get a contradiction from the assumption these values are different. Everybody happy? Where do we have unrigor? So we agree that this is true. Yeah. This is just, yeah. So maybe the only point that seems sketchy to you is whether or not this actually tends to this limit like this. Let's take a smoothing of the test function, you know? And if we take a smoothing of the test function, then all these steps are true, right? We definitely have that the right-hand side is, passed to the limit, and then everything will be fine. You know? Because G is G and its gradient are LP function, so whatever happens on a very small thing that we are changing, it doesn't, we don't care about it. You And for this step, if we have a ball, and we know that the average of function on the ball is minus some specific value is something, then if we take the average on something like this, okay, all right, yeah, all right. So it's actually, you can't deduce it from the ball. It's actually, yeah, you have a point. You can't deduce it from the average on the ball because that's a sensitive thing. But part of the Lebesgue density theorem is that you can have this. You can have this for any shape, and yeah, you can have this for any convex shape you want with the aspect ratios controlled. So what this comes down to, this Lebesgue density point stuff, comes down to best coverage covering theorem, which gives Vitali covering theorem, which means that we can cover all but epsilon of some set with this decreasing set of collection of family of sets around points, and we can certainly do that with triangles. So okay, there is more to make that argument rigorous, but this argument can be rigorous. Yeah. All right, cool. So, pleasure. Thank you for calling me out on that. So, we got a contradiction. That means we've proved the result in the case when we have a ball of radius 1. Right? A ball of radius 1, the theorem must be true. Yeah? And then everything else follows just by rescaling. So it looks like that's all I'm going to have time for. Again, leave when you have to leave, but I want to complete this. So the final board is just the rescaling, and then we'll have the Sobolev Poincare inequality required. True. For r is equal to 1 and x0 equals 0. Okay. In general, suppose we have a ball of radius r around x0 contained within our region and some function f p on the region like this. Then, let's draw a diagram. We have some ball like this, x0, radius r. Then we want to do the following. We want to define f of x0r. Actually, it's going to be annoying to keep writing that, so I'm going to just define g. So x0 and r are just fixed from now on. So let's just write g of y is equal to f of x0 plus r times y for y and the ball of radius 1 like this, right? So that for exactly localizes inside the ball of radius r around x0. Yeah? And then let's rewrite the stuff of the inequality in terms of g and see what we get. So we want, on the left-hand side of the Poincare inequality we're interested in, we have this kind of expression, f minus its average. So I'm going to write, now I'm going to write x0 because its average is actually depending on r and x0, and that's important in this case. So we have this, we are doing the Q norm, let's just write like this, dx, like this, and let us do a change of variables. So if we let x be x0 plus r of y, like this, then we have that dx, let's do everything in Rn, there's no disadvantage, so the dx is equal to Rn of dy, like this. So making this change of variables, we now do the integral on a ball of radius 1 around 0. We have f of x0 plus r times y, like this. This guy, it's going to turn out is the same as the average of g on a ball of radius 1, but we'll get to that later. We're just going to keep the constant for the time being. And then this dx now becomes Rn dy, yeah? And this is exactly the definition of the function g. is g of y. Yeah? Cool. All right, now let's look at the right-hand side of this thing that we're interested in. So let's take the ball of radius r around x0, and let's take the gradient of f of x, like this. And we're doing this to the p dx, and again, let's do the change of variables. Let's replace x by r0 plus, x by x0 plus r times y, and then this is the integral ball radius 1 around 0 of df of x0 plus r times y, like this, to the p, and then we have rn dy. But if we look what happens when we take the gradient of g of y, then the gradient of g of y is the gradient of f x0 plus r times y, and then r, right, by the chain rule. Yeah? So we can replace this thing if we divide by r. So then this thing is the same as the integral like this of dg of y p, and then this we're going to have n minus p, like this. Yeah? Cool. So let us divide by, let us consider the average on the ball of radius n, ball of radius r around x0. So this guy, the p dx, that will kill this r to the n, right? So then we'll have the average on the ball of radius 1 of g of y to the p to the minus p dy, yeah? And then let us divide by this r to the n, right? So then ultimately we have that average on a ball of radius r of x0 of df of x, the p dx 1 over p. We're taking this r on the other side, so we're going to put like this. This thing is equal to the average on a ball of radius 1 of, let's not change notation, d for g, d for the gradient, to the p dx 1 over p. Yeah? Cool. So if we look at the function, so I'm running out of time, so I'm just going to skip the actual calculation, but it's another easy calculation that this thing, that this guy, just by change of variables, is the same as the average on a ball of radius 1 of g, like this. Just change of variables. Same thing as before. So then this thing up here, right, so this is this. So then from this line, let's call this thing star. So from star, what we have is that the average on a ball of radius r x0, so we can average everything on yeah, let's divide by, let's do this in more than one step because it might seem like we're doing something sketchy. So we're going to take the take the average on the left-hand side here, so that will kill this r over n, this r to the n here. So we're going to have f minus f of r of x0 tilde q dx is equal to the average on a ball of radius 1 of g minus this thing, which we're going to define to be just g tilde, just this constant g tilde, like this, q. Now we have variable dy, like this, yeah, just from this line, yeah. So we can take the 1 over q on both sides, yeah. Cool. And then what we know, so we know by the case when p equals 1, that this thing is controlled by this thing with some absolute constant. Yeah? So then this is, let me say case 1, less than some absolute constant of this expression here. And then by this chain, or by this equality, this is the same as constant r of integral er x0 df p dx 1 over p. And that's our result, right? We have controlled the average on a ball, radius r, x0 of this function, by some absolute constant c times the radius of the ball, and then the average of the gradient to power of p, 1 over p. Yeah? So this 1 over r is just from scale, or this r power is just from scaling the ball. Nothing mysterious about it. And if you think about it, it's the natural exponent because fundamental theorem, because gradients control functions by the fundamental theorem of calculus in a line. So you'd expect this to be scaling in a linear way as we divide through. So yeah, this is the full Poincare-Sobolev inequality, and I'm overrunning, but this is all the prerequisites we need to begin the proof of Sprague regularity theorem. So thank you for your attention. Any final questions before we sign off? That's right. Yeah, this is this proof comes from compactness, so the constant c is totally out of range with this kind of a proof. Yeah. Oh yeah, these things are very important inequalities. So these constants are known. Yeah, and you get different constants for different domains. I don't know what so the constant, I think, depends on the dimension of the space, but you can have Poincare inequalities for different kind of shapes, for different kind of balls, for convex domains and whatever convex shapes, and that's a topic of research too. What's the best constant for those inequalities? And yeah, these things are known. But it's a natural thing for people to want to know. I mean, so Sobolev inequality comes down to the isoparametric inequality in the end, and maybe that's like a nicer statement that we can control the area by the perimeter, right? So area of, we have notation for area. So if we take the area of some domain with a nice boundary, connected domain with a nice boundary, then this thing is controlled by some constant of the perimeter of the boundary, where we take the scaling like this. So the perimeter is going to be an n-1 dimensional thing. So in order for this to be independent of rescaling, this is the right power. You have to take the nth root and then the nth power, right? And that's, a very much more natural thing to think about. And to me, this is a natural question. It's a kind of a natural thing to want to know. What's the best constant you can have for this inequality? Because this inequality is always true for every convex domain, for example, every convex set. And I feel the same about the constants in these kind of inequalities. It is very natural to want to know how a function is controlled by its gradient and what's the absolute best you can do with that. But this is pure math. So a lot of the things that we care about don't have immediate application to anything. I mean, the prime number theorem initially was very much a pure math theorem about distribution of primes, right? And but now has many applications in cryptography, and it's very important. But we ask these questions because we're interested in them, and that's it. So not too late to go to applied math if you're looking for reasons for why we look at these things. But But yeah, for me, these constant calculus, I like this area of analysis. I think these are interesting and hard questions, calculating these constants, these classic inequalities, and interesting things have come out from them, from that work. All right, all good? All right, see you Friday.